Hey, good morning, class. How's it going? Um, Couple quick things on today's folder. You will see at the bottom, I took a quick picture of the solutions to the workbook assignment for this chapter. So you'll find that at the bottom, and that'll help you look at the answers and work through the problems to the workbook. Also on today's, there's a video of a little demonstration that we normally do in class called the pop can explosion. So I want to go through that calculation with you, set the stage a little bit. It's in ultra high slow motion, so the actual explosion doesn't happen until about the 3 minute mark or so of the video. But in the background, you'll see a red piece of paper, a grid with 10 centimeter lines on the background. There are two pop cans that are sitting on that wooden platform. The Coke can on the left, and the Diet Coke can on the right. And then you put a firecracker in between and you explode them. So it's an elastic or a bouncing collision for momentum. So what I'm going to do is I want to go through the math calculations with you to show that momentum is conserved in a violent explosion like this. Okay? So I have the equation that will be set up like this. I have mass of Coke, velocity of Coke, plus mass of Diet Coke, velocity of Diet Coke. That's on the left. Then the explosion happens. And then on the right side of the equation, the explosion has happened. We have mass of Coke, velocity of Coke, plus mass of Diet Coke, velocity of Diet Coke can. Okay? Now, again, this is before the explosion over on the left, and this is after the explosion on the right. How much momentum is there before the cans explode? Well, their velocity is zero. Velocity is zero, so there's zero momentum over here on this side. So in other words, if momentum is to be conserved, there has to be zero momentum over on this side. And how is that physically going to be possible if both of the Coke can and the Diet Coke can are flying through the air really fast? How is it possible that they could end up with 0 units of momentum? And the answer is you just have to designate direction. One direction is positive, one direction is negative, so that one of these terms over here will be positive and one of them will be negative. Now watch what I'm going to do for just a second. I'm going to hopefully you'll agree that velocity right here and velocity here, velocity here, and velocity here are distance divided by time, right? That's the equation for velocity. Distance divided by time. And just bear with me here. I'll explain to you why I'm doing this. So that's what velocity is, distance divided by time. And I think you would all agree with me that when we freeze frame this video at the 3:04 mark is where I have it frozen for you. The Coke can over here is nothing. This hasn't been in the air at all yet. But over here, the Coke can will have been in the air for the same amount of time as the Diet Coke can. So if the times are the same, we can just look at the distances, and therefore we can use the grid on the background and not have to worry about how many seconds is it per frame or how many tenths of a second per frame. Okay? So let me put in some numbers here for you. I have the Coke can has a mass of 26.5. Let me times 0, plus the Diet Coke can has a mass of 13 times 0. And I artificially put some weight on the bottom of the Coke can just to show you. Otherwise, they should both fly the same distance if they were the same weight, right? So over here, again, we have 26.5, and it traveled, if you count over here, it traveled about 4.5 grids, or 45 centimeters. and we'll call that positive. Because Coke is better than Diet Coke, so it's got to be positive. Diet Coke can has a mass of 13, and if you went over here and counted the grids, it looks like it goes about 95 centimeters. Okay, so I did the math for you, and I get over here, and you can do this as well, 1,192.5 positive for the Coke, and for the Diet Coke, I get negative 1,235. You add those together, and you get a negative 42.5. So that's how far they off from there. There was 0 over here. It's supposed to be 0 over here, but it wasn't exact. We're not perfect, and I'm guessing the distances a little bit, right? So does this prove to you that momentum is conserved in a violent elastic collision? And you may say, well, no, not really. It's 42 off. But what percentage error is that? So if we took 42.5 units, that's how far off we are, and you divided it by the total units of momentum, that's 1192.5 and 1235. I'm going to keep that as positive. You're going to end up with about, what did I get? About 1.7% error. 0.017 times 100 is 1.7% error. So it does show you that momentum is conserved even for a violent collision like that, or explosion like that. The total momentum before, 0, was in essence 0 afterwards as well. We just have to designate one direction as positive and one direction as negative. Okay? I'm also going to have a video for you on an inelastic collision, a sticking one, whether you watch that one first or not, but I'll do a quick video for that as well.